Kube-proxy is a crucial component in Kubernetes networking architecture. Understanding its different operational modes is essential for optimizing cluster performance and scalability. Kube-proxy is a network proxy that runs on each node in a Kubernetes cluster. It serves as a fundamental networking component that enables communication between different parts of your cluster. In a Kubernetes cluster, kube-proxy runs as a daemon on every worker node. It sits between the network layer and your application pods, managing how traffic flows throughout the cluster. Kube-proxy implements Kubernetes services by managing network rules that facilitate communication to pods. It provides load balancing, maintains service-to-pod mappings, and ensures traffic reaches the correct destinations. Kube-proxy operates in two primary modes. The Iptables mode is the default, using Linux Iptables with sequential rule matching, making it suitable for smaller clusters. The IPVS mode uses IP virtual server with hash table lookups, providing better performance for large-scale deployments. The choice between Iptables and IPVS modes becomes critical as cluster size increases. We need to examine which mode scales better and understand the underlying reasons. Key factors include the number of services, backend pods, and network rule complexity. In the following sections, we will examine each mode in detail, compare their scalability characteristics, and explore recent developments in Kubernetes networking that address these challenges. In Iptables mode, kube-proxy leverages the Iptables firewall, a fundamental Linux kernel feature, to manage network traffic routing within Kubernetes clusters. Iptables is a powerful packet filtering framework built into the Linux kernel. It operates as a firewall that can analyze, modify, and route network packets based on predefined rules. When kube-proxy operates in Iptables mode, it configures specific packet forwarding rules. These rules intercept network traffic destined for a service's cluster IP address and port combination. The Iptables rules redirect this intercepted traffic to one of the available backend pods that implement the service. This redirection happens transparently at the network layer. However, Iptables has a fundamental limitation in its design. It uses a sequential rule matching algorithm, which means rules are processed one by one in order until a match is found. When a packet arrives, Iptables must check each rule sequentially from top to bottom. For a packet destined for service C, the system must first check rules for service A and service B before finding the correct match. This sequential processing results in O(n) time complexity, where n represents the number of services and backend pods in the cluster. As the cluster grows, performance degrades proportionally. These characteristics make Iptables mode mature and stable for smaller clusters, but increasingly problematic for large-scale deployments. The linear performance degradation becomes a significant bottleneck as Kubernetes clusters scale to thousands of services and pods. Understanding these limitations of Iptables mode is crucial for making informed decisions about Kubernetes networking architecture in production environments. IPVS mode represents a fundamental shift in how Kubernetes handles service routing. Unlike Iptables, IPVS leverages the IP virtual server, which is a specialized load balancer built directly into the Linux kernel. IPVS is specifically engineered for load balancing operations. Operating in kernel space, it provides direct access to the Linux networking stack, eliminating the overhead associated with user space processing. The kernel space architecture provides IPVS with direct access to the networking stack. This eliminates context switching overhead and enables high-performance packet processing that would be impossible in user space. IPVS uses hash tables as its fundamental data structure. When a service request arrives, IPVS applies a hash function to the service IP address, directly computing the bucket index where the service information is stored. This hash-based lookup provides constant time complexity, meaning the lookup time remains the same regardless of how many services exist in the cluster. This is the key to IPVS's superior scalability. The performance difference becomes dramatic as cluster size increases. While Iptables performance degrades linearly with the number of services, IPVS maintains constant lookup time regardless of scale. IPVS mode delivers several critical advantages that make it the preferred choice for large-scale Kubernetes deployments. Its constant time complexity, kernel space operation, and hash table efficiency provide the foundation for truly scalable service routing. The fundamental difference between IP tables and IPVS lies in their algorithmic complexity, which has profound implications for scalability in large Kubernetes clusters. IP tables uses sequential rule matching with O of n complexity, where n represents the number of services and backend pods. This means lookup time increases linearly with cluster size. In contrast, IPVS utilizes hash table lookups with O of 1 complexity, providing constant time performance regardless of the number of services in the cluster. IP tables maintains rules in a sequential list. When a packet arrives, the system must traverse through rules one by one until it finds a match, making the process slower as more rules are added. IPVS uses a hash table structure that allows direct access to the appropriate service entry. The hash function immediately calculates the correct location, providing constant time lookups. This performance comparison demonstrates the scalability difference. As the number of services increases, IP tables' response time grows linearly, creating significant performance bottlenecks in large clusters. IPVS maintains consistently low response times regardless of cluster size. This constant performance makes IPVS the clear choice for large-scale Kubernetes deployments with thousands of services. In real-world scenarios, the choice between IP tables and IPVS becomes critical as cluster size grows. While both modes perform adequately in small clusters with fewer than 100 services, the difference becomes pronounced in large deployments. In clusters with thousands of services, Iptables mode experiences significant performance degradation, including increased latency, higher CPU utilization, potential packet drops, and slower pod startup times. This makes IPVS the preferred choice for enterprise-scale Kubernetes deployments. While IPVS represents a significant improvement over Iptables in terms of scalability, the Kubernetes networking landscape continues to evolve with even more advanced technologies emerging. The evolution of packet filtering and load balancing technologies in Linux has progressed from Iptables, introduced in 1998, to more modern solutions like NFTables and eBPF. Let us first examine NFTables, which was designed as a direct successor to Iptables with the goal of addressing many of its fundamental limitations. NFTables introduces several key improvements over Iptables. It provides a unified framework that handles IPv4, IPv6, ARP, and bridge filtering in a single subsystem, eliminating the need for separate tools. The architecture improvements in NFTables result in better performance through reduced transitions between kernel and user space and enhanced scalability when dealing with large rule sets. Kubernetes has recognized these advantages, and kube-proxy now includes an NFTables mode starting from Kubernetes version 1.29, providing an alternative to both Iptables and IPVS modes. However, an even more revolutionary technology has emerged that promises to transform Kubernetes networking entirely: eBPF, or Extended Berkeley Packet Filter. eBPF represents a paradigm shift in how we approach kernel programming and networking. Unlike traditional approaches that rely on netfilter hooks, eBPF allows custom programs to run directly in kernel space. This approach enables programmable networking without requiring kernel modules, while providing superior observability and debugging capabilities that were previously difficult to achieve. Performance benchmarks consistently demonstrate that eBPF significantly outperforms both Iptables and IPVS modes, especially as cluster size and service count increase. The most prominent example of eBPF adoption in Kubernetes networking is the Cilium project, which demonstrates the potential to completely replace traditional kube-proxy implementations. Cilium serves as a container network interface that can completely replace kube-proxy functionality using eBPF programs. It provides advanced load balancing algorithms and enhanced security policies. The performance benefits stem from Cilium's ability to operate directly in kernel space, eliminating the overhead of traditional networking stacks and providing superior performance at scale. These developments represent a fundamental shift in Kubernetes networking architecture. eBPF-based solutions like Cilium demonstrate the potential for more efficient, programmable, and observable networking infrastructure that will likely define the future of container networking. The future of Kubernetes networking is being shaped by a revolutionary technology called eBPF. This advanced kernel technology is transforming how we approach network packet processing and service mesh implementations. eBPF, or Extended Berkeley Packet Filter, represents a paradigm shift in kernel programming. Unlike traditional networking approaches, eBPF allows custom programs to run directly in kernel space, providing near-native performance with unprecedented flexibility. The performance benefits of eBPF are substantial. Benchmarks show that eBPF-based networking can achieve latencies as low as 8 microseconds, compared to 30 microseconds for IPVS and 50 microseconds for Iptables. This represents a significant improvement in packet processing efficiency. Cilium has emerged as the leading eBPF-based networking solution for Kubernetes. It provides a complete replacement for kube-proxy while offering advanced features like native service mesh capabilities, enhanced security policies, and multi-cluster networking support. The industry is rapidly embracing eBPF technology. Major cloud providers are integrating eBPF solutions into their managed Kubernetes offerings, while the growing ecosystem of eBPF-based tools demonstrates its versatility. Additionally, Iptables is being considered as another potential replacement for traditional kube-proxy backends. The transition to eBPF represents more than just a performance improvement. It fundamentally changes how we approach Kubernetes networking, offering a more efficient, flexible, and feature-rich foundation for modern container orchestration platforms. IPVS provides significantly more sophisticated load balancing capabilities compared to Iptables. While Iptables is limited to simple random selection, IPVS offers multiple advanced algorithms and health monitoring features. In Iptables mode, kube-proxy can only perform random load balancing. When a client request arrives, Iptables randomly selects one of the available backend pods without considering server load, connection count, or any other factors. IPVS supports multiple sophisticated load balancing algorithms that can intelligently distribute traffic based on various criteria. These algorithms significantly improve performance and resource utilization. Round-robin algorithm distributes requests in a circular order. Each new request goes to the next server in sequence, ensuring equal distribution when all servers have similar capacity. Least connections algorithm routes new requests to the server with the fewest active connections. This is particularly effective for applications with varying request processing times. Weighted algorithms assign different weights to servers based on their capacity. Servers with higher weights receive proportionally more traffic, allowing optimal utilization of heterogeneous infrastructure. IPVS provides built-in health checking capabilities that continuously monitor the status of back-end servers. This ensures traffic is only sent to healthy servers and automatically retries failed connections. IPVS continuously monitors server health through configurable health checks. Unhealthy servers are automatically removed from the load balancing pool, preventing failed requests and improving overall service reliability. When a connection to a server fails, IPVS automatically retries the request on another healthy server. This retry mechanism significantly improves service availability and user experience by handling transient failures transparently. These advanced load balancing algorithms and health checking capabilities make IPVS significantly more reliable than Iptables for production environments. The combination of intelligent traffic distribution, automatic failure detection, and connection retries ensures optimal performance and high availability for Kubernetes services. When selecting the appropriate kube-proxy mode for your Kubernetes cluster, several critical factors must be considered to ensure optimal performance and scalability. The choice between Iptables and IPVS modes primarily depends on your cluster size and performance requirements. Let's examine the key decision criteria. For smaller clusters with fewer than 100 services, Iptables mode remains a reliable and stable choice. It has been extensively tested and provides adequate performance for most small to medium deployments. However, as cluster size increases beyond 100 services, IPVS mode becomes the superior choice. Its hash table-based architecture provides significantly better performance and scalability characteristics. Looking toward the future, the Kubernetes networking landscape is rapidly evolving. Extended Berkeley Packet Filter, or eBPF, represents the next generation of networking solutions, offering unprecedented performance and flexibility. When making your decision, carefully evaluate your current cluster size, anticipated growth, performance requirements, and operational complexity tolerance. Consider implementing IPVS for immediate scalability benefits while planning for future eBPF adoption as these solutions mature. In conclusion, the choice of kube-proxy mode is a strategic decision that impacts your cluster's performance, scalability, and operational overhead. Start with the mode that best fits your current needs, but maintain awareness of emerging